Okay, so last time we looked at arithmetic sequences. Today we're looking at geometric sequences, which also have explicit rules and recursive rules. So we're going to learn how to write the explicit rule and the recursive rule, and also apply them to real-world situations, and once again, convert from one to the other. Now, what makes a sequence geometric? Because remember, a sequence is a list of numbers, right? Separated by commas. Arithmetic sequences, if you remember from last time, means you're adding or subtracting by the same number every time to get the next number. While in a geometric sequence, each term is found by multiplying the previous term by the same number. So we do not have D, we have R, which represents the common ratio. Okay, so let's take a look at this geometric sequence. When we go from one value to the next, what's happening every time? I'm actually going to separate this just to make it more clear than ever. So when we go from 2 to 4, we multiply times 2. Do we do that every time? Times 2, times 2. Yes. So we're multiplying times the same number every time. So the common ratio R is 2. Now you know what makes a sequence geometric and that we're going to have R instead of D. Now, this is the formula for the common ratio of a geometric sequence. You do not need to memorize this, but again, we have key components that you need to know just in general. R is common ratio. A sub n represents whatever value you choose to look at, and a sub n minus 1 is the previous value. So in other words, to find the common ratio, you need to take any term except the first term, because remember there's no term before the first term, right? And divide it by the previous term. And you might look at this and think, well, do I really need to do all that? I can see, I know 3 times 4 is 12, and I can see that 12 times 4 is 48, and so on. But again, these lists are not always so simple. Sometimes the values are very large, sometimes they're negative, sometimes they're fractions, sometimes they're decimals. So we need to get used to using the common ratio formula. So remember, the common ratio is equal to picking any term other than the first. So I just will pick 12 divided by the previous term, 3. And that gives us a value of 4. So R is 4. And now that we know the common ratio, we could find the next term in the sequence, couldn't we? How do we do it? Well, you take your last term they gave you, multiply it times 4, and that gives you 768. So that would go right here after 192. Notice the dot means this continues on. We don't know how long this sequence is, but we know it does not end there. Time for the explicit rule of a geometric sequence. There's our geometric sequence. Here's our formula for the explicit rule. And once again, a lot of things are going to stay the same, but a lot are going to change. So let's see. A sub n stays the same always. And n stays the same because that's our variable, but a sub 1 is going to change, right? Because the first number in the sequence is different all the time. Common ratio is also different all the time. So what is a sub 1? It's the first value we see. And the ratio, we just found that a moment ago, is 4. So a sub n equals a sub 1 times r to the n minus 1. N is your variable. It stays there. And I know it is very tempting to multiply these two together, but don't do it. That breaks the laws of PEMDAS, right? Because P, E, 4 needs to be raised to these powers before it's multiplied with 3, but we don't know what n is, so that is our explicit rule. Again, if you remember from arithmetic, you could find any specific term in the sequence by plugging in a value for n. So if you want to know the fourth term in the sequence, plug in 4. Or 54, plug in 54. Whatever it is, that this explicit rule will help you find it. And I just wrote explicit equals exponent to help you keep the rules clear in your mind. Because there's also the recursive rule, and there it is. Looks very, very similar to the recursive rule for an arithmetic sequence, but a little different. What's the same? Well, you're going to have some things that stay the same every time. A sub n, a sub n minus 1, and then when a sub 1 equals. These parts stay the same. Okay, so what we need to find are the missing pieces to the puzzle, which are r and a sub 1. R, common ratio, we found it before, is 4. And what else do we have? A sub 1 is 3. There it is. So we have a dot here. You might also see it just touching where a sub n minus 1 is just right up next to it like that. Means both things mean multiply. There it is. Explicit and recursive rule. Time to practice. Find the common ratio. Can you find it? R is equal to any term divided by the previous term. I always pick the first two, but you could go here divided by this. That's totally fine too, but we will find the common ratio is 3. And you can always check this too, right? Ask yourself, is -5 times 3 -15? Is -15 times 3 -45? And so on. Okay, so we have the common ratio, and that is all we need for the explicit rule. What is the explicit rule? Can you come up with it? A sub n equals a sub 1 times r to the n minus 1. Let's plug in what we know. A sub 1, first value. Common ratio, we just found it, and then n minus 1. There it is. Really, it's some basic substitution, right? Let's keep practicing. What's the recursive rule for this geometric sequence? Well, it's really helpful to identify what a sub 1 is. First value, right? So a sub n equals what? R. Do we know R? No, we don't. Let's do it. R equals, we're getting some bigger numbers, right? You can already start to see how it's not so easy to always figure out what the common ratio is, right? If you divide these out, you will get 12. So R is 12. So we get 12 times a sub n minus 1. So what's the recursive rule? A sub n equals this when a sub 1 is that. We just wrote it a slightly different way. And now it's time for more practice, specifically here with a real life situation. So the recursive rule for this geometric sequence is given right here. Right here. And you want to look at your notes and try to write the explicit rule for this sequence. That is our first objective. Okay, you should have got a sub n equals negative 36 times 12 to the n minus 1. Was that what we had before? I think so, right? But we're writing the explicit rule, or sorry, yeah, explicit rule. There it is. Okay, 2, reverse. Now try taking the explicit rule and writing the recursive rule. This was part of our goals to convert from one form to the other. For this one, for the given rule here. Different question. Well, what do they want? Write the recursive rule. The recursive rule is a sub n equals r times a sub n minus 1 when a sub 1 is whatever a sub 1 is. Well, it depends on the placement, right? You need to look at your rules, look at your notes. A sub 1 is the value out front, so minus 2. And then we need r, right? R is right there in parentheses, 6. And now time for a real life problem. Let me see if, yes, I have it here with more room. So let's do it. Jessica Alba has a strong interest in shoes and has been collecting them for quite some time now. Due to her fame and the rarity of her shoes, the value of her collection has been increasing every year. 3 years ago, her collection was worth $375,000. 2 years ago, the value of her collection was $450,000, and last year it was valued at $540,000. Talk about appreciation. Let's assume the rate at which her shoe collection's value increases stays the same, as it has been for the past 3 years. The value of her shoe collection can be represented by a geometric sequence. The value of the collection 3 years ago is considered the first term in the sequence. So a sub 1 is, they said the first term was 3 years ago, and it's also the first term they gave us, 375,000. Okay, and they want to know what explicit rule can be used to determine the value of our shoe collection n years after that. So they're asking us ultimately to write the explicit rule. That's the big question. Okay, explicit rule. A sub n equals a sub 1 times r to the n minus 1. So a sub 1 stays, or sorry, a sub n, a sub 1 we just found, times, and usually you see this in parentheses. If you want to do that here too, that's totally fine. N minus 1 always stays the same. But what is r? That is the trickiest part of this problem. And it's not that tricky at all. Do you remember how to find r? Well, we pick any term and divide by the previous term. Well, look at this. They give us one value, the first year, and then the second year, and then the third year. Well, those you could write out as a list. 375,000, then 450,000, then 540,000. So ultimately, we can just take any value. I'll take the 45,000 and divide by the previous value, 375,000, to give us 1.2. And that makes sense, right? You could think about this logically. 375 to 450 to 540. It's going up by a decent amount, but it's not an insane amount that it's increasing, right? It's not doubling or tripling or five times anything like that, even though this is a lot of money, but it's not raising that quickly. So 1.2, remember, as a percent, you would move the decimal over two places. That would be 120%. So you'd have the initial amount, right? Let's say 375,000 plus an additional 20% to give you the 450,000. That seems accurate. It's a strong increase, but not completely mind-blowing. All right. That is it. Practice and see you next time.